Okay, so today we are going to learn about solving exponential and logarithm function or equations. There are two ways you could do it, using a calculator or algebra. So using a calculator, you just need to put, let's say there are two equations, right? y1, y2, and do second trace 5. And that's an easy way for you to check if your answer is correct or not. But when you're using algebra, there are three different ways you can do it. If variable, there are three different questions that can come with it. Variable in the base, like x is in the base over here. Same base, and you need to figure out what your value of x is. One variable in the exponent, and more than one variable in the exponent. So if there is one variable, you convert it into log form. If they're greater than one, you take log on both sides. Logarithm variable, you convert it either in exponential form or you use log laws that we talked about previously on the video. Okay, so let's try a few questions. Let's say when the variable is in the base, just like here. What you would do is you would raise both sides of the equation to the reciprocal of the exponent. So, and then you'll solve the equation. But over here, we need to isolate our variable first. So we'll divide both sides by 2. 128 divided by 2 is 64. So x to the power of 3 over 5 is 64. Now we need to get rid of our power, right? So we just need to multiply it by the reciprocal of our power that we are trying to get rid of. So 3 divided by 3 is 1, 5 divided by 5 is 1. So we get x is equal to 64 to the power of 5 over 3. So now if I were to write it as a radical, I can do cube root of 64 to the power of 5. Now cube root of 64, let's put this in the calculator and tell me what the answer is. Cube root of 64 is 4 to the power of 5 is 1024, and that's your answer. Okay, so that's how you do this question. But remember, always isolate the value of 2. Okay, let's try the next question. The steps are given to you. So the steps are that you're supposed to write both the terms on both sides of the equation as power of a common base. When the powers are equal and the bases are the same, equate the exponents, because that's an exponent rule, right? Solve for the variable, because that's what we're doing, right? So we need to make a common base here. I know that I can write 4 as 2 to the power of 2 and 9 as 3 to the power of 2, right? And 27 can be written as 3 to the power of 3, and 8 can be written as 2 to the power of 3. Now, if you see, it's reciprocal of what? My right side is reciprocal of my left side. Now, when you have a reciprocal, let's say 1 over 3, and you want to convert it into 3, you'll just have negative 1, right? So that's what I'm going to use here. So 2 to the power of 2, 3 to the power of 3, 9 minus x is equal to 2 to the power of 3, 3 to the power of 3, and my exponent is going to be over here, 3x plus 4. Okay, now I can distribute the 2's out, so 2 over 3 is 18 minus 2x, because I distributed it, and I'm going to do the same over here, so it'll be equal to 2 over 3, which is negative 9x plus 12. Let's distribute this as well, and we get 2 over 3, which is negative 9x minus 12. 2 over 3. And now I'm going to equate my exponents. I'm just going to look at these things now. So 18 minus 2x is equal to negative 9x minus 12. Isolate the variable. Let's move the 9x to the other side. So add 9x on both sides, subtract 18 on both sides. 18 minus 18 is 0. 9x plus minus 9x is 0. 2x minus 2x plus 9x is 7x is equal to negative 12. minus 18 is minus 30. Divide both sides by 7 and your answer is x is equal to negative 30 over 7. Okay. Which as a decimal will be negative 4.29 rounded to the nearest hundredth. Okay. Let's try the next question. So you're going to use laws of logarithms to solve this. If in an exponential equation the variable is the exponent, is in the exponent, you isolate the variable. So you're going to use common log on both sides to do this, and you're going to apply power law of log to bring it to the ground level, so bump and shift, and you're going to expand and rearrange. So let's see how it looks like in a question here. So I'm going to put log right over here on both sides. I'm going to bump and shuffle, so it's going to be 3x minus 4 times log 2 is equal to log 7. Now I can divide both sides by log 2. Right, log 2 and log 2 cancel. We have 3x minus 4 is equal to log 7 over log 2. Now if you remember, we can do 3x minus 7 and we can use a log law over here, or simply just figure out what the value of log 7 divided by log 2 is. Okay, which is approximately 2.807. So let's do 2.81. Add 4 on both sides, which will give you 3x is equal to 6.81. Divide by 3 on both sides. 6.81 divided by 3 is going to be x is equal to 2.27. And that should be your answer. Okay. Pause the video, try the next question. So we do log on both sides. Bump and shuffle. 2x plus 3 times log 3 minus x plus 3 times log 1 over 5. Divide both sides by log 3. And also, let's also divide it by negative x plus 3. Because we want our variables on one side, right? So when we cancel that, we get 2x plus 1 divided by negative x plus 3 is equal to log 1 over 5 and log 3. Okay, so now we solve for our what log 1 over 5 over log 3 is. So log 1 over 5 divided by log 3. Let's check. It is going to be negative 1.46. And now we have 2x plus 1 and negative x plus 3. So we're going to multiply both sides by this. Negative x plus 3 cancels out. We have 2x plus 1 is equal to, we can distribute it. We get 1.46x minus 4.39. And then we need to isolate our x, so let's subtract 1 on both sides. And subtract 1.6x on both sides. So we have 2x minus 1.46x is equal to negative 5.39. So 2 minus 1.46 is 0.54 is equal, x is equal to negative 5.39. So we divide 0.54 on both sides. 0.54 get cancelled. We are left with x is equal to negative 9.98. Okay, that's how we solve this question. Okay, let's look at another question over here. When we're solving our log functions using log laws, so things get a little bit more complicated, but it's also fun at the same time. So let's look at the steps. Using the log laws, reduce the expression to an equation of two logarithms, one on each side of the equal sign, and equate the arguments. So let's try this question. Now we know that what we can do is we can bump this and we'll get log x squared is equal to log 32 plus log 2, right? Now the bases are the same. I can also just subtract log x squared on both sides. Actually, no, let's not do that, because the reason why I said let's not do this is because my x is already isolated, right? So let's just use the log law, in which when you add two laws, log with same base, you're just multiplying it. So 32 times 2 log x. Log 64 log x. Let's isolate our log. We're going to do that by dividing it by 2. Log 64 divided by 2 is log x is equal to 0.9. Okay, and then if you want to solve it, we can basically we can convert it into an exponent because our base is 10. So it'll be 10, 0.9 is equal to x. So 10 to the power of 0.9 is x is equal to 7.94. Okay. Which is approximately 8. Okay. Sorry about that. Okay, let's do the next question here. So let's see what happens when we have all the terms which have log, but except for 1. So in this case we have 1 over here, and we know we can just do log 6 of 6, which is going to be equal to 1. So we can replace this. Log 6 x plus 4 is equal to log 6 minus log 6 x plus 3. Now what I'm going to do is I'm going to move my logs on one side by adding it to both sides. So this is going to be 0. Log 6, and it's being multiplied with another thing or added with another thing. That means I can use my log law, in which I can multiply the terms if they have the same base. So now, because my logs are the same here, I can just equate this with each other. So x plus 3 times x plus 4 is equal to 6. Let's distribute it. We have x squared plus 4x plus 3x plus 12 is equal to 6. Subtract 6 on both sides. We get x squared plus 7x minus 6 is equal, plus 6 is equal to 0. Let's use product is 6, sum is 7. My factors can be 1 and 6. So x squared plus 6x plus 1x plus 6 is equal to 0. X is factored out. I get x plus 6 plus 1, x plus 6 is equal to 0. x is equal to -1 and -6. Now, remember, always check for extraneous values. Our log can never be negative, right? So in this case, when I have negatives, I'm concerned about the safety of my logs, right? So if I put -1 over here, it would work because it'll be +3. -1 over here would give me +2, so it's fine. But if I put -6 on both of them, I'm going to get -2 and -3, which is not fine. So this is going to be my extraneous root. Okay, so remember, for these questions, always check for this, okay? Let's do our last question here. You can pause and try it on your own first. So if log base 3x is 15, then what is this log equal to? Let's figure out what the value of x is based on this. So let's convert this to an exponent. I can do base over 15 is equal to x as my exponent form. Easy, that gives me what my value of x is. Now all I need to do is put my x back into here. So it's going to be log base 3 1/3 times 3 to the power of 15. 3 to the power of 15 divided by 3 is just going to be 3 to the power of 14. So I have log 3 to the power of 14. I can bump it, which gives me 14 times log base 3 of 3, which is 1. So 14 times 1 is 14, and it's option A. Okay, we are not going to do this question since we didn't cover it in class. And in terms of application of exponent functions, just go through the questions and let me know if you have any questions about it. Pay close attention to doubling, tripling, half-life, and all those things. I can just go over it quickly here as a summary, but I won't do questions. So, applications, this is what our exponent function looks like. Y is the final amount, A is the initial amount, B is your growth or decay factor, T is total time, P is period. When you're talking about percentage growth, you're going to add 1 to it. Decay will be minus, doubling is 2, tripling is 3, and half-life is half. So you'll replace all your B's with this when it comes to it. Okay? Again, half-life is the amount of time it takes to reach half of the substance, so when it decomposes. Okay? For applications of log, we did earthquake intensity. So each increase of 1 unit in magnitude on the Richard scale represents 10-fold increase in intensity. We did a specific formula for it, which involved magnitude. So we did, if you're talking about how intense it would be 10 to the power of difference in magnitude. Same thing for loudness as well. We use the same formula. pH problems, same formula when we're looking at if it's increasing or decreasing. And then we also looked at this formula when we're comparing intensity. So the magnitude difference is this. Okay? Let me know if you have any questions about applications of log functions or exponent functions.